Welcome back to ECE 320A. We're reviewing for exam number 4 in this video, and in particular, we're working problem 8 from the fall of 2015 exam, and this is a problem dealing with finding a transfer function, and the transfer function is between this source voltage, V sub 1, and the output across that capacitor V sub 0. So we're trying to now find this transfer function, and I'm guessing that a lot of you would see this as having two meshes. So let's just try to find or write the equations in terms of these two meshes. But as we're doing that, let's see if that's actually going to produce what we need. Well, if we can now find I sub 2 of S, that's all we need to find V sub 0 of S, since V sub 0 of S will be the impedance of that capacitor, which is 1 over SC, times I sub 2 of S. And so if you're looking for partial credit, this would get you some points, drawing those two mesh currents and showing me that you understand that you can now find this output voltage in terms of I sub 2, one of those mesh currents. Really, the only wrinkle in this problem is the fact that we now have this dependent source, and if that throws you, always try to convert these problems to something that you feel comfortable with if you don't know where to go, if you're struggling. So if I was faced with this and somebody was giving me this problem on an interview and I got a little bit frustrated or flustered with the assignment, I would say, you know what, let me just go ahead for now just to give me something to not struggle with. Let me replace that dependent source with R sub 3, and I can at least show you that I can analyze a very basic circuit problem. And that would be fine in terms of getting you started. And once you start getting those blood molecules moving, those brain functions activated, those neural circuits running at high speed, then you can say, okay, now I feel a little bit more comfortable. Let me go ahead and try to analyze this with that dependent source. And that dependent source is just depending on I sub R sub 2, and I sub R sub 2 is sitting down there in the middle branch that's going up, so I could actually find I sub R sub 2, or define that, now as the net current going up in that branch, and that's simply I sub 2 of S minus I sub 1 of S. So now, if when I'm writing my mesh equations, I have to write I sub R sub 2, I know that I have a way of rewriting that in terms of the unknown mesh currents I sub 1 and I sub 2. So let's now write the two mesh equations. I now have for the leftmost mesh, I have minus V sub 1 of S plus, and I'll just go ahead and combine those first two horizontal impedances, R1 plus SL times I sub 1, and that's a function of S, plus R sub 2 times the net current flowing down in that middle branch, and that's R sub 2 times I1 minus I sub 2, and that's equal to 0. That's pretty clean. Now let me write the KVL in the second mesh. That's now going to be in the other direction in terms of voltage drop across R sub 2. So now I have R sub 2 times, and if you'll humor me, I'm going to just not include the argument S in my I sub 1 and I sub 2. This is R sub 2, and now I've already made the mistake, but this is now, I want the drop from plus to minus going from bottom to top, so I now need my net current going up is I sub 2 minus I sub 1. That's the drop from bottom to top across R sub 2, the voltage drop. Then I enter that dependent source on the left, and that's with the plus sign, so I now have plus 3I sub r sub 2 plus 1 over SC times I sub 2, and that's equal to 0. And now what I can do is now I can replace I sub r sub 2 with that expression. And doing that, now I have two equations, the blue equation and the black equation. You're not all black and blue. You're fine. Just put those into a matrix representation. You can then find or solve for I sub 2. And once you have I sub 2, you know what to do. I sub 2 will provide you with the ability to solve for v sub 0 of s, and inside that expression will be your input, and the ratio of v sub 0 to v sub 1 will be your transfer function, and you'll be done. So let's just do one more step in that process. Let's go ahead and put all of these pieces together. We have what coefficient or polynomial or expression involving r's, l's, and c's that scale r1. That's r1 plus r sub 2 plus sl. Scaling I sub 2 is the minus r sub 2, and that's now equal to v sub 1 of s. That's coming to us from the blue equation. The black equation, now we just have to remember that instead of this I sub r sub 2, we're going to go ahead and introduce I sub 2 minus I sub 1, so that now we have what terms are being scaling I sub 1. We have a minus r sub 2, and because of that dependent voltage source, we now don't have a symmetry in our impedance matrix that's multiplying the I1 and the I2. We have a minus 3 times I sub 1, and that's all we have for I sub 1. Now we have what's multiplying I sub 2. We have a r sub 2 working from left to right. We have a 3, and we have a 1 over SC, and there's no forcing function driving that second equation. Now we could actually use Cramer's rule if we wanted to solve for I sub 2. I sub 2 is now the determinant of this impedance matrix with the second column, since we're solving for I sub 2, with this column replaced with the source. So now we have, for this, we have R1 plus R2 plus SL times minus 3 minus R sub 2. We're replacing that blue highlighted column with V sub 1, 0, the source side, and then we divide that by the denominator of the impedance matrix, which is just R1 plus R sub 2 plus SL minus 3 minus R sub 2 minus R sub 2 and R sub 2 plus 3 plus 1 over SC. Now you simply have to take a couple of 2 by 2 determinants, diagonals minus, or the product of the diagonals minus the product of the off diagonals. That gives you now a ratio of terms, and voila, you now have I sub 2 in terms of your source, V sub 1, and V sub whatever we were solving for, V sub 0 of S, is now 1 over SC times I sub 2 of S, and we're done.